My menus were playing hard to get there for a second. Thank you for your patience. We're continuing in Module 1, Intro to Operating Systems and OS Structures. So we're talking about the roles, the primary functions, and then we're continuing with structures, the basic components, an orientation, and the basic structures of an OS today. I am going to post the solution right after our assignment. So sometime later today, you should see inside the module, when you click into the header, you'll be setting up a virtual machine. This won't be for 2 points, it'll actually be for 5 points. And I wanted you to be aware that there is a part of your My Campus login that you need to access. So as you get into the My Campus portal and you scroll down next to the Office 365 icon, you'll notice there's an option for Microsoft software download. You're going to want to select this, click sign in, and it may prompt you to enter another account. If it doesn't show you this, but it shows you a login screen, be sure to enter your UVI student email address, okay? Because you have a Microsoft Office 365 account, courtesy of the University of the Virgin Islands. You're going to go ahead and click through that. Good morning, Shanoa.
Good morning.
How are you?
I'm doing fine.
Glad you could join us. So I'm walking through the steps that you'll need. I'm in the Microsoft software option inside the portal. If it prompts you for a login, be sure to enter your student email address. At some point, the screen will populate, but it's been slow lately. So what I usually do is I just come over here and click software directly. And because I don't need the main screen to populate, I know exactly what I'm going to be doing. I will be in person Sunday and early next week on St. Thomas and on St. Croix for the rest of this week. So I will have copies of this image download in case you have trouble, but it's best if you get your own. I want to tell you that we'll be working with Windows Server 2022, Data Center Edition and Standard Edition, both. But the thing to understand is that the install media, the ISO or image that we download, is identical for the Data Center Edition and for the Standard Edition. The primary difference is that there's a different activation key. So essentially, you can click download. It's about a 5 gigabyte download, and it's always good to get a fresh copy. You may have a copy from a previous season. The image that you're going to want to download ends with the characters. It's kind of hard to read when I mouse over this, but you'll notice the last characters are 620 Delta 7 Echo Alpha Charlie.iso, right? So it's 620D7 EAC.iso. If you happen to have that from last semester and it's still intact and it hasn't been corrupted, that's great. And you may find that while you're trying to download that on campus, the bandwidth is faster at certain times of the day, or you may have better luck at home. But in either case, you want to make sure that what you download is this specific file. I'll have a copy of it on a thumb drive. So worst case scenario, I will be present on campus. You can just send me a text or an email. I can hand you the thumb drive and you can get a copy of it. It's the same It's the same image file for everyone. But as I said, the activation key is different. So what you want to do is obtain the product key for the data center edition, and you want to copy it to a text file. So we're going to go ahead and open up Notepad and say server 2022 data center, and then just put key, right? And then paste that. Everybody with me? And then
I
you
am.
and then you can do the same here. You can basically copy and paste, right? Only this time it's the standard edition. And all you have to do to access that is to click on the standard option, scroll down to view the key, and then copy the key or highlight it in Control C, right? And then paste that in there. Everybody has their own unique activation key. Mine's going to be in use very heavily. If you take a shortcut and borrow my key, Microsoft will know, I will know, the provost and the dean will know, the dean of student affairs will know. UVI paid for you to have your own license key, so please be sure to use your own license key. I know this is a recorded session, but anyway, I'm just telling you, all this stuff, the installation files, they kind of talk to the mothership when you start installing them. And you need to be aware that passing around license keys is a very serious violation of copyright law and incurs huge penalties. And you don't have to do that because you have your own, right? So everybody has their own. It's important to understand that. So you may recall on Tuesday we talked about, or last week we talked about the 3 different classifications of operating systems, those you pay for. Can someone offer me an example of an operating system that you pay for, you have to purchase in order to use? Hello, hello?
Windows 10.
Windows is a great example. Thank you, Luke. Yes. What about Macs? Do you pay for that software? Do you pay for that operating system? Yes or no?
Technically, yes, but it's included with the hardware.
Correct. That's what we previously established. So when we talk about operating systems you must purchase to use properly, put another way, a lot of things don't work in the operating system if you don't have a legitimate purchase, right? So it's built into the hardware purchase, it's included with the hardware, it's bundled with, but you still pay for it. That's one reason why Macs are so much more expensive. Macs also charge more because they offer free, every new version that comes out, you get free for the rest of your life, as long as you own that hardware. So it's not always true for Windows, but Microsoft started to do this when everybody started to migrate over to Macs, because they understood that is one of the very important benefits, right? In any case, there's a second version of there's a second classification of commercial operating systems. And you don't have to purchase it, but you have to purchase something in order to be able to use it. Can anyone remember exactly what you must purchase for the second classification of commercial operating systems? That's the Jeopardy theme song. Poor version of it. This would be a service and support contract. Examples of this include Red Hat Enterprise Linux, or RHEL, the only government authorized operating system of the Linux platform that is approved for use by US government agencies. Many corporations also standardize on Red Hat Enterprise Linux for that same reason. Of course, open source operating systems, like all the different flavors of the rainbow. I am partial to Debian. Debian, Debian. It's very lean. It's very void of a lot of extra bells and whistles. If you load Ubuntu or Kali, you get all sorts of extra stuff, including the kitchen sink. But if you get a Debian distribution from the Debian.org website, Debian is more of a pure kernel implementation, and there are many other distributions like Lint, like Mint and Ubuntu and Kali and so on, all these different flavors of Linux that are actually derived with the Debian kernel. If you go back further, Debian's origins lie somewhere in the proximity of something called Berkeley Standard Distribution. So it's called BSD, and BSD was one of the first created versions of Linux that derived much of its functionality from Unix. Okay, but Linux itself was created by Linus Torvalds, and it's open source completely, and it's crowdsource supported, yeah, crowdsource supported. So that means volunteers, right? All right. So as you're downloading this stuff, it will take a while, and you may or may not have a lot of success with that. But if I open the downloads page so I can see how this is coming along, I might have a 5.2 ISO on my machine by the end of the session. Any questions about this before we continue? So another thing you will be doing in order to set up your version of server software on your personal technology, you'll be loading VirtualBox. And so from previous classes, I think we've covered this before, but in case it's been a while, you want to navigate to virtualbox.org. And you're going to want to install whichever version of 6.1.36. If you have a previous version of VirtualBox on your system, you want to uninstall it completely, and then download your favorite version if you're on a Windows host or on OS X for the Mac. If you're running a Linux distribution, you can download a version to run on your favorite flavor of Linux, right? The important thing is, after you're done downloading this, you want to also download VirtualBox 6.1.36 extension pack. The extension pack provides custom ports of your specific brand and model of hardware component. So once again, the extension pack translates your specific flavor of hardware components into a virtual context so that VirtualBox runs with greater stability and with fewer mistakes or errors. I will ask you to compare the checksum, a SHA-256 checksum of your downloads to make sure that you download them. And all of this will be included in the 1.4 assignment. So I will include the SHA-256 checksums. I'll include the hash checksums for your operating system download. And if you'd like a refresher on how to do the hashing thing, my favorite tool of choice in Windows 10 or 11 is to download an app called HashTool 1.2 from the Microsoft Store option on the Start menu. And if you look up HashTool, it's free, but it also installs some older redistributables. So if you don't have any of those and then you install HashTool, it'll probably load the 2012 or 2015 redistributables. But those are still valid as long as they're updated. Be sure to update your computer. Any questions about the 1.4 assignment before we continue? The 1.4 virtual machine setup.
None for me.
Okay. So here is where we left off. This should be familiar. This is the place that we left last Tuesday, 2 days ago. And what I'd like to do is blitz as much of this as possible and then get into the chapter 2 structures content just to make sure. So one thing we said was that the closer you get to the hardware, the more privileged or more restricted the system calls, that this is often viewed graphically as a picture of concentric rings, and the innermost ring 0 is the hardware root level privilege, and then outer rings are operating system internals, and then this ring 3, ring 2 or ring 3 are the user components of an operating system, the APIs that you can write code for. And so depending on the graphic, the stuff that's closest to the user is less privileged in terms of execution rights within the operating system. Users are distinctively and intentionally isolated in their own virtual environment. And one of the key roles is virtualization, meaning every application has its own virtual computer to run in. In theory, that's what's supposed to happen. Okay, so some of this is going to be a restatement or a slightly different version of the content that we've covered to date, right? So your textbook author talks about ease of use, convenience, and types of different operating systems, and we want to make sure that we have this. So in terms of an operating system definition, how do you define an operating system? Well, it's a resource allocator, right? So it manages resources. It's a control program. These are other perspectives about how to view an operating system. Once again, your textbook author is coming at it from the computer science side of things, where Arpasi Dussault and what we reviewed last week was more like hardware oriented. There's no universally accepted definition. That's why the term firmware is also equivalent to operating system, right? So when you have an intelligent device and it has some basic code that loads when you turn it on, because it's a digital or connected device, it'll have this embedded software that's referred to as firmware, and that is precisely, it is a low-level operating system, right? Everything a vendor ships when you order an operating system is a good approximation. Again, don't forget Gaddis includes things like the development environment and the operating system utilities and so on. You always have something running under the hood when an operating system is loaded, when a system boots. When it starts up, the services that are running constantly are the host and system account services and processes. And those tend to be part of the internals, sysinternals or kernel, right? Everything else is either a program or an application. So when you boot a system, there is a very low level, and we're going to learn this when we talk, we're going to learn more about this when we talk about file system. But when you're starting up a piece of hardware, it's going to load from a chip or from a file known as a UEFI. It's a bootstrap program. And it loads into memory, and that's what starts the hardware access and virtualization process, right? So there's a post or power on self-test that's part of this. Again, we'll talk more about that in detail. So this is the author's version of what we covered in early classes about the von Neumann diagram, right? So all of these components are constants. You always have a controller. You always have some kind of memory. You always have input-output devices. Any questions? I/O devices and the CPU can execute concurrently. That means simultaneously. That has to do with multitasking. Concurrency is one of those three functions. CPU moves data. Here, this is just an explanation of how the von Neumann diagram works. Here, the device controller informs the CPU. This is really important. This concept, the interrupt, this prevents everything from executing at the same time and crashing the computer. The term interrupt is associated with hardware devices, which is why device controllers use this resource and function to control how hardware devices coordinate their access, right? So interrupts, we're going to talk a lot more about that. You don't have to know all of this for your Module 1 assessment, but the idea that hardware devices are associated with interrupts, that's useful information, and that might be in your assessment. You transfer control. This gives you more information about how interrupts work. A trapper exception is a software-generated interrupt. So interrupt has to do with hardware, but something that works like an interrupt executed through software would be called a trap or exception. We just want to make sure everybody's on the same page, right? An operating system is interrupt driven, meaning for an operating system, most of the coordination and collaboration at a low level is hardware operation and coordination, right? So if you have an application that says, hey, I need the printer now, that's done through a trapper exception. But when you actually get down to the physical hardware, an interrupt takes over, right? So you have these layers that you have to deal with. Does everybody understand that concept? From the diagram where you have users, applications, operating system, hardware, right? So an application says, hey, I want to see this on the display. It's going to trickle down into the operating system, and then it's going to go out to the device. And then by the time you're pushing graphic images out to the hardware, that's interrupt, right? Interrupt handling. So you can really get into the weeds on this. Again, the first two chapters in our first module is intended to be overview. So I want you to understand that polling and vectored interrupt system has to do with interrupts, right? So polling is a concept that has to do with interrupts. In turn, interrupts have to do with hardware and devices and device controller. Any question? I know I'm moving kind of fast. So this is just a graphic explaining how the CPU clock cycles coincide with and are used to structure the timing of cutovers between IO devices when those interrupts are executed, right? You don't have to know this, but it's just good information. A CPU clock cycle is what ultimately determines how many and how rich your multitasking environment can be. If you have a slow CPU, you don't have very many things you can juggle. IO structures. So this is generic information about how input output is processed by the operating system through system calls. This is all pretty low level stuff. And when we talk about the device controller, there's a status table in memory that contains its state. So an IO device could be busy, it could be sleeping or in power save mode. Everybody understands what I'm talking about, right? Could be disconnected. If you have an IO device that isn't plugged in, if you have like a USB drive that was there and is no longer there, but you have a shortcut on your desktop and you click the shortcut, but the USB device is not connected, right? Everybody understands what I'm talking about, right?
Yeah.
Okay. Yes, storage definitions and notation review. So this should be generic review. A byte is 8 bits. Binary digits. That's the contraction that created the word bits. 8 of those is a byte. 1,024 bytes is 1 kilobyte. 1,024 kilobytes is a megabyte. 1,024 megabytes is a gigabyte, terabyte, petabyte. Now, what do I need you to know? Disk manufacturers and USB manufacturers, they tend to operate with even numbers and they don't use the 24, 24, 24, 24, 24, which is why when you buy a 1 gigabyte hard disk and you format it properly, it never turns out to be a full gigabyte. The manufacturers just round off and say, oh yeah, it's 1,000,000,000,000,000,000 if you're dealing with gigabytes or terabytes, right? RAM, the idea is that you have persistent RAM or non-volatile RAM. RAM is volatile, so you have to use the disks to store what would otherwise be volatile data. If you don't, when the power goes off, the RAM dies. Yeah, solid state disks, more popular, very popular. In fact, there are fewer and fewer regular hard disks that are sold. Caching is one way to speed up. If you remember from CSC 241, we talked about the memory speed hierarchy and how you went from static RAM, it's a cache on the chip, to level 1 cache and level 2 cache on the die, meaning on the actual socket, right? The thing that plugs into the socket. The further away from the CPU you get, the less volatile it is. The closer you get to the CPU, the more volatile it is. Caching is the 80-20 rule. Everybody remembers 80-20 from computer architecture, CSC 241. Can anyone state what the 80-20 rule means? Yes, go ahead. Somebody was going to say something about 80-20. The concept of caching is a very common phenomenon. Efficiency experts have discovered that 20% of your resources are used 80% of the time. So it might be easier to remember if you said it's really more like the 20-80 rule. 20% of your resources are used 80% of the time. Caching means you're putting those 20% closest to your workspace. They're preloaded into the memory or they're stored closer to the CPU because you're going to use them more often. That's what caching is. Does anyone need me to repeat that? The most used information is stored closest to where it's used. All right, that's just common sense. The most commonly used information is stored closer to where it's used and with faster memory methods. Device drivers. Now this is huge. Device drivers are the software components that allow a custom hardware device to operate efficiently with a standard CPU and disk, right? And memory. So you have all these millions of different devices and models, and in order for that to work right, device driver, you have to know how to make low-level system calls, privileged system calls, and device drivers are often require security measures because if hackers embed stuff in a device driver, they can get in on the ring 0 or privilege level of the operating system and embed themselves with something called a kernel level exploit. So yeah, storage device hierarchy. This should look familiar to you, although its actual diagram in CSE 241 was different. Please tell me this is ringing a bell. Please.
Yeah.
Okay, all right. Caching, so it talks about caching. There is a significant benefit when RAM memory is accessed directly by the devices. Now, in the von Neumann diagram, the memory is over on your left, the input-output devices are on the right, and what's sitting in between? CPU, right? Direct memory access means that certain devices can access the memory directly without having to go through the CPU first. This is a really important concept to understand clearly. So what we're saying is that you, from the von Neumann diagram, and here's the von Neumann diagram, right? Ordinarily, whenever you're running to and from memory, you're working through the CPU. An innovation for operating systems was to include something called DMA, or direct memory access. What it means is that special input-output devices, such as hard disks, video cards, high-performance network cards, that input-output device can push and pull data to and from RAM directly without having to go through the CPU first. That's what it means, okay? That's an important concept. Any questions about DMA? Or direct, that is a hardware and an operating system innovation that's very important to understand.
I'm good.
Okay. Yes, so I'm kind of hoping this is all pretty basic stuff. I just want to make sure we don't leave any stones unturned. So when we're concurrently operating, we have this idea of a thread of execution, and you have multi-threading or hyper-threading. That means you're juggling more than one, right? They could be isolated processes or they could be integrated processes. This is something I'm kind of recalling from the other author, right? Instructions and data in memory. So this is just a different way of representing the von Neumann architecture. Am I going to try to trick you on your exam or on your assessment? No, I'm not going to throw this diagram. However, I would still encourage you to study this diagram because it's a fresh view of von Neumann, and there are some subtleties that would occur from this diagram that you don't get from the other one, like interrupts. Hello. IR devices, right? IO requests and interrupts. That's kind of important. And so see here, you see the device going straight to the memory. That's a good overlay of how DMA works on the von Neumann diagram. And I said I wasn't going to put that in your assessment, but I'm actually kind of loving this right here. All right, you get the point. It's good to be familiar with that. So yeah, we're reviewing computer system architecture. You need to be familiar with computer system architecture in order to use operating systems well. And remember that some have multiprocessors. Now, when you have multiprocessors on a motherboard, it's not unlike having multiple cores on a single chip. The point is that you have more than one processor to work with to compute. This increases the complexities of operating system calls, obviously, because you can have these different types of operation. What do you need to know? I'm going to say that you need to know this for your assessment. The difference between asymmetric multiprocessing and symmetric, meaning, and actually in your computer architecture course, we go into SIMP, MIMP, and all that kind of stuff. This is a simpler version of it. It's clean, and it's a good review. Each processor is assigned a specific task, and that should be a C right there. So if you have a task and it's on one processor, and each task has a separate processor that's asymmetric multiprocessing, that's pretty easy to implement in an operating system. Much more difficult is to work symmetric multiprocessing. Each processor performs all the tasks. And so here it's talking about, it's giving you a graphic representation of how this works with the computer architecture, right? So each of these CPU cores and their respective registers and cache each have this direct link to and from RAM. Multi-core chips are very common. So similar concept, right? Core 0 and Core 1, as opposed to CPU 0 and CPU 1. Same thing. It's just packaging, basically. Now, the computer engineers would be doing backflips at this point and going, "No, Professor Kentop, that's not that simple. You're oversimplifying. Having multiple processors with multiple cores is a much more challenging operating system problem to solve than multiple cores." And I'm like, yeah, it's not. Allow me to illustrate. You can have 3 Xeon processors. See, when you work in IT for 25 years and you're a certified systems engineer, you view this through a different lens. So let's take a different look at this. Let's say I have a Xeon processor, or a Xeon processor. Everybody with me? Hello. I need to hear from somebody.
Yeah.
Okay, or let's say I have an AMD Athlon processor. Typically speaking, with multiprocessor architectures, you never see them with odd number of processors. It's always 1, 2, 4, 8, 6, something like that. It's an even number of processors. It's never like this diagram. Each of those processors in turn has cores. So what's the difference for an operating system that's running this kind of platform versus an operating system that's running that kind of platform? Well, each of the Xeon or Athlon chips, the packages have multiple cores. Let's pretend that each has 12 cores in a server CPU. So I would have 12, 24, 36 cores total. As opposed to an AMD Threadripper, a beast, which has 32 physical cores hyper-threaded, so it actually has 64 virtual cores. Now, which one has greater performance? Well, that depends on how finely tuned the operating system is designed and whether or not it can operate that way. In general, the more chips and the more cores you have to coordinate, the less efficient it is because you have overhead when you're breaking down a computing task to run on each of those separate chips and then separate cores. If you have one chip and then one set of cores, then in theory, conceptually, it's a simpler thing to accommodate in an operating system. Any questions?
None for me.
Okay. All right. Well, that's probably very intuitive and all common sense, right? Clustering. So let's talk a bit about clustered systems. We'll get into this quite a bit more when we get into the file system module. But I want you to know you can get whole servers that work in tandem together. There are multiple copies of the same data on each of those servers, and they have to synchronize the information between them. That requires clustered services in the operating system. So if you're going to be running clustered systems, you need to run an operating system like, I don't know, Microsoft Server 2022 Data Center. Okay. And if you're not running clustering, then it's probably better to run Microsoft Server 2022 Standard Edition. Does that make sense? Because in a data center, you'd have a bunch of identical systems that are running for failover, for redundancy, right? Now, when that's set up, you usually have diskless systems, and there's shared storage. It's called a storage area network. So you have disk volumes that are stitched together, and they run in tandem as well. RAID 0, RAID 1, we kind of covered this, and we'll go over this more when we get into the file system. But I just wanted you to know asymmetric clustering. One machine has a hot standby mode, meaning it's one primary that's doing it, and then there's a standby system over here, but it's not really handling the load. That's similar to the asymmetric model we just talked about, where you have one task running on one CPU and having the same task running on multiple CPUs. If you have symmetric clustering, it means that all of them are running that same resource simultaneously. This one it's simple and it's efficient, and if the main system dies, then the one that's on hot standby just takes over, and there's a heartbeat in between. So the one that's on standby is monitoring for what's called a heartbeat for the system that is actually handling the live task. So it's alive and it's working. There's a heartbeat, there's a heartbeat, there's a heartbeat until it's crashed. And then the second one goes, oh, I don't have a heartbeat, and it kicks in. So the heartbeat thing is consistent with asymmetric clustering implementations. I am not going to get into the rest of this. We're going to keep moving very quickly. Yeah, the storage area network, it's called a SAN for short. We'll get into that later. Just know that this is associated with clustered systems, right? For now. Multiple programming and job scheduling in order to coordinate all these things. So here are the different ways of concurrence operations. Again, we'll be doing deep dives in each of the modules over this. So there's all sorts of ways to share a resource. One of the most common is time sharing, right? Where you have so many slices of time in a minute or a second that you use that are dedicated to a specific, and there's a swapping thing going on there. Yeah. Virtual memory is huge. So virtual memory is a really big deal. Can we stop for a second, please, for a short break?
Sure.
Okay. Stand by. So obviously, for this introduction to operating systems, you're getting a preview of coming attractions. Memory management will be a dedicated module all by itself. And there are several chapters devoted to memory management, but what we're really doing here is walking through each of the components of our computer architecture, right? So we talked about CPUs, now we're talking about memory. And this is RAM and the address schemes used to work with RAM efficiently. How many of you remember the torture that you endured in CSC 242? Did you ever wonder, am I ever going to use that stuff? Well, the short answer is you're going to reference some of that information when we get into memory management methods, because some of that stacks versus heaps, everybody remembers some. Does that sound a little familiar? Stacks versus heaps? Something like that?
Yeah.
Yeah. So interrupts keep hardware from crashing, software interrupts, exceptions or traps keep software from crashing. So a good example of a software error would be division by 0. It's not impossible. You were raised to think that division by 0 is impossible. No, it's possible. It's just disastrous. Okay. It just blows stuff up. And that's one thing that, you know, infinite loops, it's very easy to create an infinite loop. So how do you do that? Here's the quick and easy version that causes all sorts of problems. Kids, don't do this at home. Let's say that you have a Gmail account over here. And then over here, you get a free Hotmail or Yahoo Mail account. And then you set up a forward between the Gmail account and the Hot or Yahoo Mail account. And then on the other side, you also set up a forward between the, on this side for the Gmail account, so that anything that's received by this email is forwarded to where that email. Well, you'd be shocked at how often little software algorithms like that are possible. So somebody starts beaming a lot of email messages this way, and then as soon as they reach here, all the email over here is forwarded over there, and all the email over here is forwarded over there. And if you have very simple algorithms, it's not long before 2 messages become 4 messages, become 8 messages. You get the point, right? It just gets bigger and bigger and bigger and bigger until the internet crashes. Yeah, okay. Which is why we have those things like exceptions. And yeah, now you have it. Dual mode operating, we talked about kernel mode versus user mode. This is ring 0, that's ring 3. That's privileged closer to the hardware. That's on the application side where the users are. So those are 2 common points of reference for many operating system schemas. When we say schema, we mean how we're talking about the skeleton or structure of an operating system. So privileged mode is lower level. Less privileged is out by the user. That's the main thing to know there. When you have this virtual machine manager for guest VMs, that comes into play when you're working with, we'll talk about the VMM when we talk about VirtualBox. And when we start using virtual machine functions, you have a host system, that's the physical hardware system. You have guest VMs, those are the virtual computers that are running inside the host. So just be sure you understand what those terms mean and what they're about. Any questions?
No questions.
Okay, so part of the operating system process is to operate as much as possible in the user realm. In fact, there's a whole philosophy about how to create a stable operating system by minimizing what's in the kernel so that ultimately everything that's really needed is working out here with the user. We're going to go into that more detail when we talk about kernel dynamics, but essentially, when you have a microkernel architecture, what you're doing is structuring or designing the hardware level of the operating system to a very minimalist approach, right? So that the bare minimum is handled by the kernel, and you push everything else for system calls out to the user. And other operating system architecture incorporates something called the monolith. It's just a very large kernel, and you don't. There's more stuff between ring 3 where the user is and ring 0, and it's kind of all chunked together in that kernel. So it's a really big, really expansive, really extensive set of resources and system calls in that kernel. And most of our current operating systems use the monolith approach, the monolithic approach. We'll get into that more later, but yeah, kernel mode, whenever you're operating in the kernel mode, you're very low level hardware, near the hardware, and it's extremely privileged. And you have to be very careful about how you control those things, or the system crashes. So process management, when you have memory and CPU working together on an actively running software application, now you have a process. So part of our operating system exploration concerns the wonderful world of processes. And in Windows, a process is called a service. And in Linux, does anyone know what the special name for a process is? Does anyone know what the special name is in Linux for a process? A running process in Linux is called what? It's not called a service. That term is kind of reserved for the world of Windows, right? Well, it's just a standard term, right? So if you have an active running process in Windows, it's referred to as a service. And then services can have a single or multi-threaded aspect to them. We're not going to talk about threads right now, but yeah, you have a PC. A PC, in reference to this context, is not the personal computer, it's the program counter, right? So daemon, D-A-E-M-O-N, sounds like demon, sounds like the devil. Linux, active running processes in Linux are called daemons, D-A-E-M-O-N. Everyone say daemon. Hello? Hello? Are we there?
I am.
Okay. You did hear that, right?
Yeah, someone got disconnected. I think it was Luke.
Okay. Process management, right? Has to do with the program counter, right? The PC. And when people see that, they think personal computer. They get confused. Don't let that happen to you. So processors have an active thread. You can have a process without a thread, or at least one primary. We'll get into that more later. Well, there's a whole series of process management resources that have to be there for an operating system to work right. So let's review. CPU, memory, right? Memory management, process management. The two go kind of hand in hand. So that's why concurrency concerns the CPU and RAM hardware more than anything else. And so these are essential concepts about memory management. It determines what's in the memory, keeps track of which parts of the memory are currently being used and by whom. If you have an efficient operating system and a secure operating system, those details are journaled. The term is called journaling. If you have a journaling operating system, it means you have the ability to log or audit those things that are running. And that's really important. So that kind of memory management has to be built in from the ground up as you're designing the operating system. And there can be very lean feature impoverished operating systems. We'd call them firmware, very limited functionality. But then you also have operating systems that are incredibly robust, and they have a lot of these features. So now we're getting to the storage management piece of this, right? So if you think about this, we're kind of retracing the same ideas and concepts we introduced last week with the von Neumann model. We have the file system piece, the persistence piece, right? So we have virtualization, we have concurrence, and now we have persistence. Storage management. So memory management, process management, storage management, those are like the big three, yeah? And all right, so the OS provides a uniform logical view. The term is hierarchy. This is a word you're going to see a lot. The word hierarchy means you have main components, then subcomponents, then smaller subcomponents, then teeny tiny mini micro components. And if you have a big to small organization framework, another word for that is hierarchy. Has anyone taken biology? Has anyone had biology?
Only in high school.
Okay. Do you remember the classification system for biological organisms? Kingdom, phylum, subphylum, class, order, family, genus, species?
Yeah, I remember that.
Okay. Yeah. So that classification schema is a hierarchy. You have main directories or root, you have the root directory, and then you have main directories and then subdirectories and then subdirectories, and that's what they're saying. So things, when you talk about backing up data, free space management on a disk, that's disk defragmentation and disk cleanup. That's what we're talking about right here. The same things that you're doing for assignment 1.2 intersect with this interest right here. And so there's a reason why we're doing this hands-on activity. It's because we're going to be talking about temporary or swap file memory management that utilizes disk storage to supplement RAM storage when an operating system is multitasking too much and it has to juggle and it has to make space, and there is no more space. There's no more main memory. Where does it go? It goes to a disk subsystem, which is closer to the RAM than otherwise. And so that's kind of virtual memory. It's make-believe RAM, only it's on a disk, and it's closer to the RAM because it's on the front of the disk as it's spinning. It's kind of complicated, but we'll get into that. Any questions? You see these terms, primary, secondary, tertiary. Primary is the closest to the CPU, secondary is further out, tertiary is, whoa, that's good for backup stuff because you can take an optical disc or magnetic tape offline and home with you. Write once, read many. So a lot of these main ideas or general concepts, it's important to be familiar with them. But the finer points we're not going to get into until we get into each of their respective modules. So here's the performance continuum, which is kind of like the memory continuum you saw earlier. The further away from the CPU, the slower it is, right? But the more massive it is. So the size increases as you get further away from the CPU, but then the access time decreases dramatically, okay? And look at this bandwidth. 100,000 megabytes per second, not bits, bytes. That's gigabytes, terabytes, right? So you can really move a lot of data. So yeah, this is a good graphic representation of file system management or persistence and disk storage management that an operating system does seamlessly. We don't even think about it. The operating system does all this in the background. So what am I saying? All of this is done automatically in the background. We don't even think about it. We just know that we can use our screens. There's a little bit of lag time. Whenever there's a little bit of lag time, it's pulling something from slower storage, right? Here's the part that gets to be sticky. In a distributed computing environment, you can have more than several copies of a piece of data, and that's also true in a singular computing system. You can have a copy of it on the hard disk. It can be loaded in the main memory, in the cache, in the hardware register. And if there are changes, those changes have to propagate up and down the chain. This kind of thing can be terribly disastrous if your operating system is poorly designed. And so it says, yeah, chapter 17, that's way down the road. Closer to Christmas is when we're going to be getting into some of this, okay? Input-output stuff, spooling, caching, buffering. Those are terms that mean temporary storage. Isn't this typical? I'm sorry, I don't mean to lose it, but most of you know that one of my primary interests here at the University of the Virgin Islands is not operating systems or networking or hardware. It's cyber security. And since this is the dinosaur book and it's been around 30 years, this is the part of the dinosaur book I love. It's like, of all the things, the privileged ring zero, closest to the hardware, crash ready, most unstable part of the operating system that hackers love to mess with. The protection and security piece is where? At the very end of the book, at the very end of the course. It's an afterthought. This is one of my pet peeves about operating system design. There are a few operating systems that are designed that I can cite, a couple of versions of Linux actually, and there are a few versions of Windows that are pared down. They have a smaller footprint, and the protection and security piece was the intentional thought up front, and it's why they have a much leaner, cleaner, smaller footprint. They don't have all the bells and whistles, okay? Excuse my rant, I'm just sharing an observation, and this is why we have operating system instabilities, is because the protection and security piece of an operating system is something that a lot of operating system design process considers at the very end instead of intentionally up front. Okay. And where are we in terms of time? Are we getting close to the, oh, we're at 12:15. Let me see how close we are. So protection and security. I'm just gonna zip through these screens very fast to determine whether or not we're gonna continue with this on Tuesday or jump into chapter 2. Kernel data structures. Oh, there we go. CSC 242. Didn't I say CSC 242? Right? Didn't you do something with a tree and didn't you talk about trees in CSC 242? Somebody? Anybody? Yes? No? Maybe? Okay, maybe not.
I don't remember.
Yeah. All right. So data structures have to do, are closely aligned with protection and security. So, right. So here they're talking about generically in the marketplace, the computing environments. You can have firmware and so on. I think we've already talked about this. You have light firmware versions, right? Augmented reality. I'm sorry. I didn't even click that. Client server computing systems. We've already mentioned that. Said something about it. You have a server operating system versus client operating systems. Peer-to-peer operating systems. So a lot of times firmware devices are very adept at client networking or peer-to-peer networking. So there's usually a networking component to peer-to-peer because in order for that to work, you have to, so P2P networks is a big deal. Everybody's heard of the dark web, right? Virtualization, we're talking about all of the different innovations that have to do with running a virtual machine inside a physical hardware machine. We've mentioned aspects of this. The last few slides talk about the different industry leaders. There's a free and lean version of virtualization you can get, like VirtualBox, but it's for servers. It's called Zen Server. VMware is a commercial product, right? Citrix is a commercial product. But Zen Server has a free version you can use. We'll be talking quite a bit about VMs, but that is, yeah, all right, I'll tell you what, we'll pick up on Tuesday with virtual machines. From here, we want to talk about the 2 different hypervisors and the 3 different types of cloud computing environments, okay? Are there any questions before we close out the period? I know this was a blitz. I know this was a blitzed review and there was a lot of content and we didn't really speak to specific student learning objectives, but there is an awful lot of content to cover in the introductory module. So any questions about the stuff that we've, the general concepts we've covered for each of those areas? Again, this is a preview of coming attractions for what you're going to see throughout the modules later in the course. If I don't see you before the weekend, please enjoy a safe and pleasant weekend, and we will see you in class on Tuesday. Keep your eyes peeled for the 1.4 solution assignment later today.
Awesome. And Professor Kentop, you'll be in